Okay, hi folks, we're back and we're halfway through Unit 2, so it's time for simple harmonic motion. So we're going straight to Mr. Davies' interactive PDF of past papers. There's simple harmonic motion there, and we're going to have a look at a couple of questions from 2022 and 2019. And as usual, make sure you have a go at the questions first and then come back and see how we have done them. So this is question 10 from the 2022 paper. A student is studying simple harmonic motion and they're using a mass oscillating vertically on the end of a spring. And we have to state what is meant by simple harmonic motion. Well, this is a definition straight from your course notes, and it's that the displacement of the oscillating mass is proportional to and in the opposite direction to the unbalanced force acting on the mass. Or, alternatively, you could have stated the acceleration instead of the unbalanced force. There's the marking instructions. And interestingly enough here, you could just have written the relationship from the relationship sheet, F equals minus ky, because that too is just a statement of what simple harmonic motion is, albeit in equation form. Part B, the vertical displacement of an oscillating mass on a spring can be described by the expression y equals a cos root k over m times t. Now, that is in the same form as the relationship on your relationship sheet, y equals a cos omega t. And omega there will be equal to root k over m. And then we're told the symbols have their usual meaning, so y is the vertical displacement, a is the amplitude, k is the spring constant, m is the mass, and t is time. And we've to show that this expression is a solution to the relationship m d2y by dt squared plus ky equals 0. Now, you might not be familiar with that relationship, but if we have a closer look at it, then d2y by dt squared is the second differential of displacement, which is acceleration. So therefore, we can rewrite that relationship as ma equals minus ky or f equals minus ky, which is of course the relationship that we use to describe simple harmonic motion there. Displacement's proportional to and in the opposite direction to the unbalanced force. So we've to show that the above relationship y equals a cos omega t is a solution to the relationship f equals minus ky. So this is a purely mathematical derivation here, and we're going to use a simplification to help us and state that omega equals root k over m. Now, if we want to get to a relationship that's got acceleration in it, and we're starting off with a relationship that's got displacement in it, then we're going to have to differentiate the displacement with respect to time relationship twice. So let's do that. If y equals a cos omega t, then differentiating dy by dt will be equal to, well, if you differentiate a cos curve, you get a minus sine curve. So it will be minus a omega sine omega t, using your rules of differentiation there. Now, dy by dt is velocity, but if we differentiate again, we'll get d2y by dt squared, that's acceleration, and you differentiate a negative sine curve, you'll get a negative cos curve, and multiplying by omega again, we'll get minus a omega squared cos omega t. Then if we do a little bit of rearranging, d2y by dt squared will be equal to minus omega squared a cos omega t. Now, we simplified things by stating that omega was equal to root k over m. That was what we did to simplify things at the start. So what we should now do is substitute the root k over m back in again. So omega squared will be equal to k over m. And then a cos omega t becomes a cos root k over m times t. And then if we simplify even further, then d2y by dt squared is equal to minus k over m times y, because that was the expression right at the start. Y equals a cos root k over m times t. And then we've just got a last wee bit of algebra to do, where we're going to multiply both sides by m. So m d2y by dt squared is going to be equal to minus ky, and therefore m d2y by dt squared plus ky is equal to 0. And that's it. That's the relationship that we had to show. It's a kind of strange version of the simple harmonic motion relationship, and it highlights the requirement for a calculus approach because displacement's always changing, velocity's always changing, acceleration is always changing. There's the marking instructions there. So first mark for the double differentiation, and the final mark for showing the rearrangement and showing that final statement. That's pretty tricky. Part C. A mass of 0.75 kilograms is suspended from a spring of negligible mass as shown in figure 10a, and the mass is 0.75 kilograms. And the mass is now pulled down through a vertical distance of 0.038 meters, is then released and allowed to oscillate about the equilibrium position. The spring has got a spring constant K of 24 newtons per meter, and by considering the expression y equals a cos root k over m times t, we've to show that the angular frequency of the mass is 5.7 radians per second. So it's a show question, and it's a relationship that you're maybe not too familiar with. But remember, y equals a cos omega t is on your relationship sheet, so omega must be equal to root k over m. And the first thing we've to do is find omega, the angular frequency. So if omega equals root k over m, the spring constant is 24, and the mass from the diagram is 0.75 kilograms. If you do that on your calculator, you'll get an answer for the angular frequency. Omega equals 5.7 radians per second, and that is what we had to show. Now we're going to need that in the next part of the question, because we're going to determine the maximum acceleration of the mass. Straight to your relationship sheet, a equals minus omega squared y, and we know what omega is. We've just worked it out. It was 5.7, so it'll be minus 5.7 squared times the displacement we were given in the question was 0.038 meters. That's the vertical distance that it has been pulled down from its equilibrium position. So at 0.038 meters, that's when the acceleration will be at a maximum. And if you do that on your calculator, you'll get an answer of 1.2 meters per second squared. And you might be wondering, should I put a minus sign in my answer? Well, you can put it in if you want. You can leave it out if you like, because the maximum acceleration will be 1.2 meters per second squared vertically upwards and vertically downwards when the mass is at its extremity positions. And in part 3, this is on the axis below, sketch a graph showing how the acceleration of the mass varies with time for the first full oscillation, and numerical values are required on the acceleration axis only. Well, we've just worked out what that acceleration is, and it's plus or minus 1.2 meters per second squared. So let's put them on the y-axis. And remember, the acceleration is a maximum at the extremities. So this mass has been pulled down the way through a vertical distance of 0.038 meters, and then it's released. So because the 0.038 is positive, then its initial acceleration will be in the opposite direction to that, which will be negative. So I'm going to start my graph off at negative 1.2, and it's going to be a negative cos curve. Now, drawing a negative cos curve is pretty tricky, so I'm going to use the magic of some editing here, but make sure it starts at negative 1.2, it goes up to 1.2 and back down to negative 1.2 again. And it should be a negative cos curve. Let's have a look at the marking instructions. So see part 1, that was where we had to show that the angular frequency was 5.7 radians per second. See part 2, we worked out the maximum acceleration. And see part 3, There's our negative cost curve drawn as a smooth single line, and the additional guidance there tells us it's 1 mark for the values of the maximum acceleration and 1 mark for the shape, which could be a cos or a negative cost curve. Pretty tricky question, methinks. A lot of maths in there, but let's have a look at another one. This is the 2019 paper, Simple Harmonic Motion again, and this time it's question 11. A home improvement shop has a machine that can produce paint of any colour, and small amounts of pigment are added to paint in a tin. The tin is then shaken to produce a uniform colour of paint, and that machine is shown in figure 11a. So the paint tin is going to oscillate in the vertical direction with simple harmonic motion. The tin is placed in the machine and clamped securely, and during shaking, the oscillation of the tin in the vertical plane can be modelled as simple harmonic motion. And the tin of paint has got a mass of 3.67 kilograms. The tin is shaken at a rate of 580 oscillations per minute, and the amplitude of the motion is 0.013 meters. And for A part 1, we have to show that the angular frequency omega of the tin is 61 radians per second. Straight to the relationship sheet then, and omega equals 2 pi f. But in this case, we don't know what the frequency is in hertz, but we do know there's 580 oscillations per minute. So cast your mind back to National 5. Frequency is the number of oscillations divided by the time. So we can substitute that in for the frequency, 580 divided by 60. And when you do all that on your calculator, you'll get an answer of 61 radians per second. And that's what we had to show. A part 2, calculate the maximum kinetic energy of the tin. Well, the maximum kinetic energy will be when the displacement is 0. It will be when the tin is at the equilibrium position, because the kinetic energy is 0 at the extremities and it's at a maximum in the middle. So if we go to our relationship sheet, then kinetic energy is a half m a squared minus y squared. And then let's substitute in everything that we know, bearing in mind that y is equal to 0. Well, the mass is 3.67 and the amplitude is 0.013. And if you do that in your calculator, you'll get an answer of 1.2 joules. Let's have a look at the marking instructions. There's A part 1 with the show question starting off with a relationship, and then subbing in the 580 oscillations per minute to get the angular frequency of 61 radians per second. And A part 2, the kinetic energy relationship, where y is equal to 0. That's a standard 3-mark question, 1 mark for the relationship, 1 for the substitution, and 1 for the final answer with the correct units. Then 11 part A part 3, or III as some people might say. Now remember, when Roman numerals are used, it means that the different parts of the question are connected. So we're going to need the answer from 11A part 2 to do 11A part 3 here. So on the axis below, sketch a graph showing the variation of the kinetic energy EK of the tin with the vertical displacement y from its equilibrium position, and numerical values are required on both axes. Well, we know what the maximum kinetic energy is. It was 1.2 joules, and that is in the middle where y equals 0. And the kinetic energy is going to decrease as we go out to the extreme displacements. That was 0.013 meters, both in the positive and in the negative direction. So, if we look back at our little diagram there, the maximum kinetic energy is in the middle, and the kinetic energy is going to be 0 at both extremes, at the very top and at the very bottom of its motion. So at plus 0.013 and negative 0.013. So if we go from 0 kinetic energy up to 1.2, and then from 1.2 back down to 0 when it reaches a positive displacement of 0.013. And if you're wondering why it's a curve, well, if we look at the kinetic energy relationship, you can see that the kinetic energy varies with negative y squared. So it's an inverted parabola with a positive y-intercept. Wee bit of extra maths there for you. Once again, the maximum kinetic energy is when the displacement is 0, and 0 kinetic energy when the displacement is plus or minus the amplitude. Part B, a coin falls onto the lid of the tin of paint as it's being clamped into position, and the coin loses contact with the lid during the first oscillation. And we have to state the magnitude and direction of the acceleration of the tin when the coin just loses contact with the lid. Well, if we imagine that the tin starts oscillating and moves downwards first, and the acceleration of the tin is directly proportional to its displacement. So as the displacement increases, the acceleration is going to increase, but the coin is only resting on the top of the tin, and therefore when the acceleration of the tin reaches 9.8 meters per second squared downwards, the coin is going to lose contact with the surface of the tin. Or in other words, the coin is going to be in free fall due to gravity, but the tin is going to have an increasing acceleration downwards as its displacement increases. That's pretty tricky. In fact, that might make more sense when we do the next bit as well. So part 2, we have to determine the magnitude of the displacement of the tin from its equilibrium position when the coin just loses contact with the lid. Well, the relationship that links acceleration with displacement is this one here, A equals minus omega squared y. So if we sub in for an acceleration of 9.8 meters per second squared, and it's the magnitude of the displacement that we're looking for, so we don't need the minus sign. And omega was 61 from the previous part of the question, and don't forget to square it. And then we're going to rearrange and find y. So y equals 9.8 over 61 squared, and that gives us an answer of 2.6 times 10 to the minus 3 meters. Let's have a look at the marking instructions. So B part 1, there's our 9.8 meters per second squared downwards, and B part 2, using our acceleration of 9.8 meters per second squared when the coin loses contact with the tin, then we get our answer of 2.6 times 10 to the minus 3 meters, and because it was the magnitude of the displacement we were looking for, then the minus sign is bracketed, not required. Okay, that's a couple of simple harmonic motion questions. Pretty tricky though, and a lot of maths in there. And next time we're going to have a look at a couple of travelling wave equation questions. We'll see you in the next one.